All right, we did have one question on one of the molar conversion problems. So this is on the worksheet from last time, section 4. We'll just do the first one. It says, how many fluorine atoms are in 38 grams of CF4? Tells us the molar mass is 88 grams per mole. So we're going to start with what we know. We have 36 grams and we're looking for how many fluorine atoms. So, sorry, not 36, 38 grams of CF4. Y'all with me so far? Okay. So we're going to use the molar mass to convert grams of CF4 into moles of CF4. So 88 grams of CF4 on bottom so that the grams cancel to 1 mole of CF4. And if I lose you at any point, let me know. All right, now we learned last time, we dealt with water, but it doesn't matter what compound we have. This is a 2 atoms of hydrogen to 1 atom of oxygen ratio, right? What we learned last time, it's a 2 mole to 1 mole ratio. Do you want me to go through without that proof, or just, how do you want me to go about it?
I'm not even sure. I guess just.
I'll show you the easy way, and if you want me to go through the in-depth, then I can.
Sure.
Okay?
So that, by the way, if you make that calculation, it's 0.431.
And you're for this here?
Yes.
Okay. And that's, you could always do it that way. Find an answer and do one step at a time the whole way. And that works, no problem. But I just continue with this conversion factor. If we have 1 mole of CF4, then we have 4 moles of F, right? But then we want to know how many atoms, so we do have to convert that to atoms. So for every 1 mole, so that goes away. For every 1 mole of fluorine, we have 6.022 times 10 to the 23 atoms of fluorine. Does that make sense?
It's the multiplying by 4 that I don't understand. Because I thought that was represented already within the 38 grams.
Okay, let me do it a different way.
Is the molar mass not just the individual C and F atomic weights added together?
It is. It is. So let's do it a different way.
Because it almost seems like when you're multiplying it by 4, that's including the carbon that's in there, and we only care about the F.
Okay, this might make a little bit more sense. Yeah.
Well, it's because, like, right, correct me if I'm wrong, for every 1 mole of CF4, there's 4 moles of fluorine, because there's 4 atoms, and mole is a measure of the amount of particles.
Right.
Yeah. So then that's why you multiply it by 4, because if you have 1 mole of CF4, you have 4 moles of fluorine.
I'm going to do it slightly different. It's the same math, but watch. So if we have 1 mole of CF4, we have 6.022 times 10 to the 23 molecules of CF4. Does that make sense in your mind?
Yes.
Okay. And so this goes away. And if we have 1 molecule of CF4, how many fluorine atoms do we have?
Oh, there's 4 of them.
Does that make sense? 4 atoms of fluorine. So I just swapped these. Either way works. In fact, this is probably a more straightforward way to do it. So that goes away and you're left with atoms of fluorine. Good?
Yeah, I mean, I could follow the logic. It just seems intuitively wrong to me for some reason, but that's all right.
Sorry. Anything else? Any other questions on conversions or aqueous solutions? All right. We don't have a whole lot left for this unit, and we'll probably finish a little early. I hope that doesn't upset anybody. All right. Oh, Nick, you hate it? Okay.
We had plans.
All right.
Let's just make it longer.
Okay. I'll just go extra slow. Just kidding. All right. Let's see. I'll have to think about that, see if I can. Okay, so today we're going to talk about concentrations. We talked about, we know what concentration is, yeah? If something is highly concentrated, it means what? Has a lot of that stuff in it, right? In comparison to the whole. So concentration. I'm going to just give you an equation rather than a definition. Is that okay? Because I feel like this is more useful. And this is the equation for concentration no matter what unit we're talking about. This is how you calculate concentration. It is the amount of solute over the amount of what you have, the solution, right? Does that make sense in everybody's mind? So this is how much solute we have in regards to the whole solution. Good? And if you're not sure of the equation, because we're dealing with different types of concentration, it's like, oh, what's the equation for that? You can always come back to this. It's always going to be the amount of solute over the amount of solution. All right, so let's talk about the main type of concentration that we use in chemistry. Is called molarity. And molarity it's still the amount of solute, but we say it's the number of moles of solute over the liters of solution. And so the unit of molarity, so capital M is the symbol we use for molarity. Don't get that confused with mega, okay? It's not a prefix. And the units are moles over liter. Not moles over milliliters, not grams over liters, but moles over liters every time. Okay? And so you'll be given questions on the exam where it might give you the mass of solute and it might give you the volume in milliliters. Convert mass to moles using molar mass, and then convert milliliters to liters using the prefix conversion. Are we good? Okay. So let's do an example. Any questions with what molarity is? All right, so if we have 3 kilograms of sodium chloride in 2,500 milliliters of salt water. Okay. What's the solute? First of all, what's the solution? What do we call the solution? Salt water. It's a homogeneous mixture of salt and water. You with me? And that's what the definition of solution is we learned last time. Okay, so that's our solution. And what is the solute? Salt. Solute.
Is that 31 or 38?
It's 3 kilograms. My bad. Tell your teacher how to learn how to write. Okay. We good? So we need to calculate our concentration in molarity. So where do you want to start? We can do this a few different ways. I'm going to show you the simple, that's the more work way first. The way people think about it originally. When I say people, I mean the majority of the time, okay? So we can convert 3 kilograms of salt, NaCl, into what? In the end, what are we looking for? We want, so when it says molarity, we're looking for moles over liters, right? We can convert that into moles. Before we convert it to moles, we convert it to grams. We don't want kilograms, so that goes down at the bottom. Oh. And there are 1,000 grams in a kilogram. We okay so far? Okay. And then we can convert these grams into moles using the molar mass. This is 22.99 plus 35.45, 58.44 grams of sodium chloride. Y'all with me, or did I go too quickly? To 1 mole of sodium chloride. And we can find an answer here. 3 times 1,000, 3,000 divide 58.44. Somebody tell me what that is. 51.3? Okay. Moles. Did anybody else get that? Okay. All right. Then we can convert this 2,500 milliliters into liters, right? So 2,500 milliliters of my solution. And we have 1,000 milliliters of solution to 1 liter of solution. And that gives me 2.5 liters of solution. I have moles, I have liters. Now what do I do? Divide them. This is moles of solute, this is liters of solution. That's what concentration is. And we get 20.53 moles per liter, or we can just say this is 20.53 molarity. Good? That makes sense in everybody's mind? Do we have any questions on that so far?
Units of molarity is just M.
The symbol of molarity is M, capital M. You can do it either way.
Okay.
Molarity means moles over liters. This is a simplified version to write it, but whenever you're converting, use moles over liters. Okay. Now we can see I used this much room to get that, yeah? Now, if I put it together, use this equation right here. It's amount of solute, and how much solute do we have? 3 kilograms. And we have 2,500 milliliters of solution. So this is amount of solute over the amount of solution. Now, I'm not saying one way is better than the other. It's all preference, okay? Just because I like one way doesn't mean you have to like it the same way, okay? Now I'm going to convert one at a time. I can start with kilograms or I can start with milliliters. It doesn't matter. So if I start with kilograms, because it's on top, and that's how we read, but it doesn't really matter. 1 kilogram of sodium chloride has a mass of 1,000 grams. Y'all with me? And then the molar mass of sodium chloride, we just figured it out, is 58.44 grams to 1 mole. Now I have moles per milliliter. So now I keep going. I don't want milliliters. 1,000 milliliters on top to 1 liter. Milliliters goes away. Now I'm left with moles over liter. The math is the same. But now it just puts it all together. What way should you do it? The way that comes to your brain. Okay? So we're still going to get 20.53 molar solution of sodium chloride. Good?
Could you actually make a saltwater solution with 3 kilograms of salt and only 2.5 liters?
Maybe not.
Just wondering.
That's pretty highly concentrated. But with salt, you might not be able to. So maybe that was a bad example, but
It was a great example. I mean, we still figured out the math. I just was wondering.
yeah. Probably wouldn't happen.
So molarity is concentration?
Yeah. It's the, I guess you'd say the SI unit of concentration. But like everything, there's other units too. And we'll learn about the other ones today. And then we'll learn how to convert from one unit of concentration to another unit. Okay? So a lot of conversion today. How are we feeling on conversions? Stoichiometry, dimensional analysis we're okay with? Okay? To get good at this, guys, show all your units. I know it takes a lot of space, takes a little bit more time, but like I mentioned last time, I was getting some other things ready for next unit, and I decided I wanted to take a shortcut to just quickly do something, right? And I took that shortcut, and it ended up taking me a lot longer because I got it wrong the first 3 times. It's like, what? What's going on? I know I'm doing this right. Okay, so show your work. Show all of the units. And see that they cancel out. If they all cancel out except for the units we're looking for, we got this. Okay? And you can still make mistakes by if we I don't know, calculate this wrong, right? We can still make a mistake. So you just got to be careful. Any questions so far? Okay. Let's do another example. Okay. If we have 250 milliliters of a 1.5 molar concentration of hydrochloric acid, I want to know, well, how many grams of HCl do I have? Guess I wrote that a little bit wrong, but how many grams of HCl do I have? So we're basically using molarity as a conversion factor. Remember, molarity is moles over liters. So we could just say this is 1.5 moles of HCl to 1 liter of solution. Right? Okay. What is this? 250 milliliters of what? Of a solution with concentration of 1.5 molar. Good? And notice how I say that. 1.5 molar concentration, because it sounds goofy to say 1.5 molarity concentration. I don't know, maybe it all sounds goofy because it's new. But that's how we read it. All right, so let's start. Where should we start? With what we know. And we know two things. We know 250 milliliters and we know 1.5 molar solution. I like to start simple. Molarity means moles over liter, that's 2 units. Milliliters, that's just 1 unit. Does it matter where you start? No, it doesn't. Okay? So 250 milliliters of my solution. And then I have this conversion factor here. But what do I have to do before I use that? Change it to liters, because this is not in milliliters. And that's the thing I was making a mistake with in that example that I told you that I was working on. This was a certain unit, and my conversion factor wasn't in that same unit. And I just wasn't paying attention about canceling. I just went through and I got it wrong several times, okay, before I figured it out. So 1,000 milliliters to 1 liter. Hope we're good at that one yet, or so far. So now we have liters of my solution, and if you want, you can find an answer before you start the next one. You really can do that. And if that helps, do it. Just break it up into sections, do it, okay? Does anybody want me to do it that way? Okay, let's do it. Then you're going to have to do some calculation. In fact, I can do this one on my own. 0.25 liters of solution. Okay, that's what I get. So I'm going to start with 0.25 liters of solution. And now I'm going to use this conversion factor. 1 liter of solution to 1.5 moles of HCl. Liters goes away, and I can find an answer here. Is this my end answer yet? No, because I'm looking for grams of HCl. And the way I like to do it, I like to just run it all the way through. But if you like to break it up just to give you a little breather, then do it, okay? So 0.25 multiply 1.5, what is it? Point what? 0.375. Yeah, and this is why calculators come in handy, because sometimes I do that all the time. I think, oh, I know this. And you guys see me do it a few times already, right? So use a calculator, and this is moles of HCl. Not our answer, so we continue. So I'm gonna start with 0.375 moles of HCl. And I'm gonna convert that to what? Grams. The molar mass is 1.008 plus 35.45, so that is 36.45-ish, rounded, but maybe 4.6 if you want to be better. Okay, so that is grams of HCl to 1 mole of HCl. Any questions on that stuff?
Yeah, you lost me as well. I had also calculated that if it was 1.5 moles of HCl to 250 milliliters, then it would be 6 moles of HCl to 1 liter, right? Because you just multiply.
But we only have 0.25 liters.
Yeah, right, but you have 1.5 moles and 2.25 liters. Wouldn't that mean that there's more moles in per 1 liter?
You have, let's see,
Because that's a quarter of a liter, so 1.5 moles in a quarter liter would be 6 moles in 1 liter.
but this says we have 250 milliliters of this concentration. If we have 0.25 liters, it's still the same concentration.
Yeah, right, but wouldn't they both, like if you increased it to 1 liter with the same concentration, wouldn't that mean there's 6 moles? Because you multiply.
Per liter.
Per liter,
Mhm.
yeah, 6 moles per 1 liter, so just where did the 0.375 come from? That's where I'm lost.
So we did 0.25. Do you understand this 0.25?
Yeah,
0.25 multiply 1.5, because now this is 1.5 moles still per liter. So now liters goes away. So it's a quarter of 1.5.
so was the concentration then, oh, so 1.5, the capital M is moles per liter? That's okay.
Yeah,
That's
yeah.
what I was missing, okay.
Yes, capital M. Whenever you use it as a conversion factor, change it to moles per liter, always.
Got it.
Otherwise, it will wreck you and throw you off.
Mhm.
Gavin, do you have a question?
No, I was just gonna make a point that might help them to find moles. It's, in the real chem it says it's just the liters solute times molarity, which is exactly that.
Yeah.
And that's how we get moles, and then we convert moles to grams.
Okay.
Yeah, thanks, that makes sense.
Yeah.
I just missed that, you know,
So good. Thanks for pointing that out,
Mhm.
because hopefully it helps somebody else. All right, so moles go away, and we're left with grams. So we do 36.46 times 0.375, and we should get about 14, and it's actually 13.7, but we have 2 sig figs, so we should round to 2 sig figs. Good? So you can break it up into 3 sections, no problem. But if you're okay with just going all the way through like we normally do it, that's fine too. Your call. There's no right or wrong way, it's just a preference. Any questions on this?
I have a question about the exam, so,
Mm-hmm.
it's multiple choice, there's not gonna be like an option of 13.7 and an option of 14.
If there is, whose team am I on?
Ours.
Yours, okay? Yeah.
Depends on.
Well, it also depends on if they say,
Calculate to appropriate sig figs.
yeah, so you do have to follow that. Uh-huh.
Remember the last problem, the what we found the molarity of the original, the 3 kilogram one?
Yeah,
Our final answer was 20.53, correct?
yeah.
fix, cause we only have 2.5 liters.
Let's see. Yeah, I probably didn't follow this. So we should probably just use 1 sig fig. So what is it, 20?
21,
We'll look at 2 6 figs.
Yeah, it'd have to be 20. Yep. Good. Everybody understand that? Okay. Good catch. All right. All right, let's do one that's kind of like the question we did at the first of class. Let's say we have a if we have 5.65 molar concentration of sulfuric acid, and we want to know what is the concentration of H plus. And a lot of times we just say that's bracket H plus. This means concentration of H plus. Okay? So we want to find the concentration in molarity of H plus. Some of you guys can probably just look at this and say what it is. But let's go through this. So we got to convert molarity of H2SO4 into molarity of H plus. Good? So break this down, 5.65 moles of H2SO4 to 1 liter of solution. Whenever you're converting, always change molarity to moles per liter. We okay with this? All right. Now, if we just ignore this part right here, the 1 liter of solution, and we're going to convert moles of H2SO4 into moles of H plus. If we have 1 mole of H2SO4, how many moles of H plus do we have? It's real similar to the question we talked about before. How many? 2. 2 moles of H plus. That goes away. And now we have moles per liter of H plus. We're done. We took something that looked a little to not too bad. And if you can see that, great. If you can't, then we can change moles to molecules and molecules to particles, and then right, we can do that. But we don't have to. Because it turns out the 6.022 times 10 to the 23 will just cancel anyway. Do you want me to show it the other way? Okay. So if I have 5.65 moles of H2SO4 to 1 liter of solution, and then we have, for every 1 mole of H2SO4, we have 6.022 times 10 to the 23 molecules of H2SO4. Good so far? Okay. And then if we have 1 molecule of H2SO4, how many hydrogen ions do I have? We have 2 ions of H plus. Oh, but I want moles, right? Okay, so let's get rid of that. And for every 6.022 times 10 to the 23 ions of H plus, what do I have? 1 mole of H plus. You following me? And that goes away. What else goes away? So what did I do? I just multiplied by 2 anyway. So if you can see that from here, it's going to save you a ton of effort. If you can't, no big deal. You'll still get the right answer. Okay. And so we get here 10, what is that? 11.3? Yeah. Molar concentration of H plus. Questions on that? All right. You guys all picked up this worksheet? Would anybody like to do some on your own for a minute?
Sure.
Okay, so this is. So we did section 1 last time. Section 2 says calculate the molarity of the given information. And section 3 says calculate the volume of the solute or the mass of the solute given the molarity, and this is kind of what we just did. So section 2 and section 3 we should be able to do, and even section 4 we just did. Does anybody want to go over another one together? Or do you want to try some on your own? Whatever you want.
Can you scroll to the right?
This way?
Yeah. How come, we had 6.022 times 10 to the 23rd on there twice?
Because first we converted it to molecules, and then we converted from ions to back to moles.
Oh,
So this is the same mathematically as that.
oh, okay, you just like showed.
Showed the long way to do it. And we showed this proof last time, and if you understand this proof, you don't have to keep proving it anymore.
Oh, like, okay.
So you'll see one of each of these types of calculations on the exam. So there's 3 questions right there.
So essentially, like the big picture idea is that if we need to find a specific atom in a molecule, we just always multiply that atom by how many there are by the amount of like moles for the whole molecule.
Mm-hmm. Yep. So for water, it's 2 moles of hydrogen to every 1 mole of oxygen.
So what confuses me by that is like, how could the molarity for a single atom within a molecule be larger than the molarity of the entire molecule? That's just why it
Uh.
confuses me. Like, I understand what you're saying conceptually,
Oops.
but it's like if the H2SO4 is 5.65 molarity, but then H positive ions are 11.3, that's like a bigger number.
Mm-hmm.
So like, why is it that way? It just seems weird.
Because it's a 2-to-1 ratio. of hydrogen ions to hydrogen sulfate ions.
Well, I understand that, but wouldn't, like, a part of, like, a singular part, like, logically, wouldn't a singular part of, like, an entire molecule be smaller?
I know what you're saying, let me,
It's the exact same issue I have with
mm-hmm,
So there's a larger number of hydrogen atoms, but the molecule itself is like larger than those. So even though there's like a larger ratio of hydrogen atoms to the rest of it, those are smaller in comparison to like the actual number of moles, like the
So,
molecule itself.
yeah.
Okay, so we're saying that, like,
So,
it's just a measurement of the amount of atoms.
remember moles
Okay,
are different. If you have a mole of sugar, you have this much sugar.
right,
You have a mole of water, you have this much water.
okay.
So, same thing with, this is sulfuric acid, and this is hydrogen. It's still a mole, right?
Yeah,
And so you have 2 moles for every one of these.
so
And
like,
so your number's gonna be bigger.
so like 11.3 molarity of the hydrogen ions can be like this, but of the whole concentration can be like that if it's 5.65.
Yeah.
Okay,
Can you scroll up a little bit?
that makes sense,
Yeah.
thank you.
This way?
Yeah.
At some point,
What's that?
at some point, will you do the, one of the ones in 4?
Yeah.
Like the one of the ones with the OH in parentheses?
Like, which one do you want to do? I'll do
Like
whatever
that
one you want.
0.08 polarity.
Okay. Yeah. Let's do it right now, unless you guys aren't ready. Who wants more time on your own? Okay. Give you a minute or two.
Well, use the periodic table that we're gonna get on exams, would be my recommendation.
Is that what it is?
2.99.
How are we coming? Yeah.
We do, section 2, number 2, or
So this one right here,
Right above it.
right above it. We'll do that one after we do this one right here. Is that the one you wanted? All right. So it says calculate the concentration of, in this case, OH minus, because it doesn't have any H pluses, for each strong acid or strong base. So, and we didn't get into strong acids and bases yet. We'll do that next unit, but this is the same, just a topic that we use for that. Okay, so we have 0.8 molar concentration. I can rewrite that as moles.
0.08.
0.08, thanks. Moles of aluminum hydroxide. Do you understand what I did there? Per 1 liter of solution. Okay, and we want to know what's the molarity of H plus, or sorry, OH minus. Okay, this is what we're looking for. Okay, so for every 1 mole of aluminum hydroxide, how many hydroxides do we have? 3 moles, right? And that goes away, and we're left with moles of hydroxide to liter. And that is molarity. Good?
Yes.
Okay. So it's just going to be, multiply that by 3, and you get 0.24, but we need 1 sig fig. Good?
Good. Thank you.
Okay. Any questions on that one? Okay, next question. Yeah? No?
We have a question on section 2, first problem.
Okay, we're going to do the second problem, and then we'll do the first problem.
Okay.
Good enough? So 10 grams of sodium hydroxide, and we want to find the molarity. This is in 1.5 liters of solution. Is this the question, Nick? Okay. So our question is, we want to know molarity. And what's another way of saying that?
Moles over liters.
Moles over liter. Okay. We have grams and we have liters. Grams of solute, liters of solution.
What number is this?
This is the second one in section 2.
Oh, I see.
Okay. So do you want me to do it in one problem, or do you want me to break it up in one section at a time?
No problem.
Okay, I'll let Nick choose.
That's how I'm able to problem.
Okay. So we got 10, the amount of solute is 10 grams of NaOH. The amount of solution is 1.5 liters. Following? Okay, now we're set up, now we just convert. Liters, we want to stay liters, so we're good. So we just convert grams into moles. So we find the molar mass of sodium hydroxide, which is 22.99 plus 16 plus 1.008. You following? You don't have to memorize those numbers, guys. They're on the periodic table. But as you do these and do these and do these, you start to memorize them, okay? And if you don't, no big deal. So the molar mass of that is what? 40? 40 grams of NaOH. Is that what everybody got?
39.998.
Okay, so round to 40, good enough. If you don't round until the end, that's okay too. That's probably better. Okay? To 1 mole of NaOH. That goes away. And now we have moles per liter of NaOH. That's what we're looking for, so we can stop converting. And we get 10, divide 1.5, divide 40, should give us 0.1 molar solution of sodium hydroxide. Good? Yeah.
I think we need
0.166.
Section two, right?
The
Okay.
molar mass of that molecule is 39 grams, or 39, not 40 grams.
39 exactly?
39.998.
Yeah, so like basically.
Okay. So let's do it again. You're probably right. Maybe I made a
He is right.
mistake. So I rounded this wrong? Okay, yeah.
Well, we're,
So, yeah, if we get this and we round it to 1 sig fig, it should be 0.2 molar solution. You're right. Thank you. Good catch. We good? Yeah, he has on. What?
Three, number one, section three, number one.
After we do section 2, number 1. Okay? Yeah.
just forgetting what we different answers and what's on the key.
Oh, yeah, me too, what'd you get?
Oh, so what you're saying is I made a lot of mistakes here?
Not 684
Yeah.
moles.
Okay.
Yes, that's why I got
We're getting
two
point
moles,
two.
you have to,
Okay.
if you put the grams on top, it gets,
Yeah.
you get 684.
So what you're saying is I need to go back and redo my key. I apologize. And no, this brings up a good point. Do you know why there's so many mistakes on this?
It's 'cause it's AI.
No, actually, no. AI made the worksheet, and then I came back later and put the answers in. So why did I get them all wrong? Because I was going too fast. Really? That's why. So when and I had another student just take an exam and he says, oh, I went too fast and he got a lot wrong. How many times do we do that? Everybody does that. So slow down, take it easy. Okay? All right. So let's do, yeah, that's a lot of molarity. I was thinking that was kind of high. Maybe I should have just checked a little closer, huh? 5.85 grams of sodium chloride in 500 milliliters of my solution. Okay? We good so far? Now we got to convert grams into moles and milliliters into liters. So we got 58.44 grams of sodium chloride to 1 mole. Did I do that? Did I remember that right? Okay.
Yes, correct.
And then, so we have moles, and now we do 1,000 milliliters to 1 liter. And what do we get? 0.2?
Yes.
0.2, okay.
I thought I was doing it wrong.
Yeah, it probably is. Yeah. Wow. I was just a little bit off. We're fine. Sorry, guys. NaCl. Yep. Okay. What other ones did I make a mistake on? The first one in section 3? Someone say that?
Hey, you can't do that,
Yeah.
because I have some.
Yeah.
I see how you did that, Professor. When I typed it in exactly like the way you did, I got 684 molarity. Whenever I did like 5.85 divided by 500 divided by 58.44 times 1,000.
That's what it is.
But that's what it
Is that right?
No, you put 584. That's what I got when I did that on my calculator.
You got 0.2?
No, I got 584 for that the first time.
You mean 684?
684, sorry. Yeah, 684.
Let's see here. So 5.85 divide 500 multiply 1,000 divide 58.44.
You multiply by 58.
Yeah, it's 0.2. That's right.
Exactly what I
Okay.
did. Yeah, you multiply by 58.44. That's how I got this.
See?
It's funny because I was going really fast.
Easy to make a mistake. Be careful. Be careful. All right. Number 3, section 3, the first one, section 3, Yazan? So 0.5 molar solution containing, we want to find, in this case, the volume, right? So this is moles of sodium chloride per 1 liter. And we have 5.85 grams of sodium chloride. Where do you want to start?
Convert the 5.85 grams to moles.
Sure, I like to start here because it's the simplest. 5.85 grams of sodium chloride. And we've done this a few times already today. Grams of sodium chloride to 1 mole. Okay, so now we're at moles, yeah? Now we can use this but flip it. You see that? So 1 liter of solution to every 0.5 moles of NaCl. And somebody do the math, make sure I didn't goof. Should be 0.2 liters or 200 milliliters. Is that right? Woohoo, I got one right. All right. One for me. Just kidding. Sorry. Okay, how are we feeling? Yeah.
We're finding moles first, and then we're.
Could I have done that in different order?
Yeah.
Sure.
I think that's where I missed, because I didn't flip the.
Yeah, and how do you know to flip it? Because if you didn't flip it, units wouldn't cancel out. So you got to make sure you write those units down to make sure the units cancel appropriately.
So is that moles divided by molarity gets us the,
Sure. I don't like to think of it that way, because then, I mean, I don't mind if you do. I don't mind if you think of it that way. The reason I don't is because then I have to remember is that, okay, moles divided by molarity is volume. And some of you can do that because to tell you the truth, most of you guys are smarter than I am. Really. A lot of people think smartness is knowledge. It's not. Okay? If your brain thinks, I'm sure all of your brains think different than mine does. And that's okay. So, yeah, do it that way. But in my brain, in fact, yeah, I used to work at a print shop. I think I told you that before. Worked at a print shop, and I had to make some copies for a customer that they wanted it they wanted it blown up by 290% or whatever. Like, okay. I can't just do it in my head. I can't just. I have to know what I'm doing is right. Otherwise, I try something, and it makes it wrong. There's a waste. Someone has to pay for that, and it's probably me, right? So I have to get it out and write it out and make sure I know it's right. That's me, okay? And I know we're all different. So, yeah, do what works for you for sure, okay?
Volume, moles over liter divided by moles.
moles over molarity equals volume.
Well,
correct?
I don't know.
Well, yeah, that's.
I don't memorize stuff like that. I don't. But my units tell me they cancel out appropriately. Tells me, yeah, that's right.
I guess I should just think about volume being liters and then figure out how to get to liters.
Yeah, that's what it is.
Yeah.
It's-
Okay.
It's moles. over
Are we good so far? Are we ready to move on, or do we have other questions? All right, let's move on. All right, how to dilute. We talked about what it means to have a diluted solution, right? How to dilute a solution. you add water, right? Okay, but we want to know how to make a particular concentration, okay? So I'm going to start with a little graphic. If I have some water in here and I put red food coloring in it, it's going to look something like that, yeah? What if I add water to this? What's it going to look like?
Lighter pink.
But more of it, right? So something kind of like that. Y'all with me? Which one has more food coloring in it?
They're the same amount.
Oh, the same amount. All I did was added water, right? One of them has more water than the other one. That's it, okay? So I can say this is n number of moles. And this is, over here, a different number of moles. Or is it the same number of moles of red food coloring? The same, right? So N1 equals N2. You with me? And we just use for number of moles, and we'll get to more of that next unit as well. And over here we have a let's use a different color. Concentration 1, and over here we have concentration 2. Do they have the same concentration? Which one's higher concentration?
The one on the left.
One on the left has more food coloring per unit of water, right? And then we can do the same thing. This is a certain volume, and this is a different volume. Yeah? Now, let's compare volume and molarity to the number of moles. What's the relationship? Well, so molarity is moles over liter. What do I need to do to this to make it number of moles?
Multiply by liters.
You with me? So molarity times liter is equal to the number of moles. Okay? And here's probably what you guys was talking about, right? All right. So if this is true, then we can also say M1V1 is equal to M2V2. That true? So whenever we dilute a solution, this is going to be true. So let's know that formula. And I don't know if that is on the reference sheet. Let's check. It is? Oh yeah, okay. Yeah, it's on there. So that's one less thing we have to put on there, but we still have to know how to use it, right? Let's do an example where we use it. Okay. So here's in fact, let's say we want some hydrochloric acid. But on Monday, we need a 0.2 molar concentration of hydrochloric acid. And then on Tuesday, we need a 3 molar concentration of hydrochloric acid. And then on Wednesday, we need a, 2.5 molar concentration. Should we go to the store and get all these different concentrations? No, what should we get? High concentration or low concentration?
High concentration.
If we make high concentration, we can dilute it to make whatever concentration we want. Does that make sense to everybody? Just add water to it. Okay? So I go to my stock room, and I have 12 molar concentration of HCl. And by the way, when you take the lid off of this, It gets rid of all of your nose hairs. So if, in fact, next time, I'll bring some. If anybody, don't get a wax job, and we'll get it taken care of. Okay? No, I'm just teasing. We won't do that. But it really, very, very corrosive material. All right, so let's say we want to do an experiment, and we need 250 milliliters of a 0.5 molar concentration of HCl. How are we going to make this? We're going to use this equation right here. Okay? So what do we call this, M1 or M2? It doesn't matter. But just thinking about it logically, this is what we start with. We can call this M1, right? And this would be M2. And what's this right here? The 250 milliliters. Volume 1 or 2? 2. That's how much we have of our molarity 2. You with me? Okay. And so what can I find with this information? Volume 1. How much of this stuff do I need in order to make this? Make sense? Okay. So now I grab my equation and I solve for V1. We got M1 V1 equals M2 V2. Should I plug my numbers in then solve, or solve then plug my numbers in?
I would solve symbolically.
It doesn't matter, but I remember when I took physics for engineers at the U long time ago, and I was in the discussion, and the TA was saying, yeah, it's better to solve it symbolically first. I wasn't used to that. I was saying, I don't like that. I don't like that. And I decided, you know what? I'll try it. I'll definitely try it. So I tried it. It's way better, guys. So don't take my word for it. You guys do whatever's good for you, okay? So I'm going to divide both sides by M1. And I got V1 is equal to M2 V2 over M1. Can you still make mistakes doing it this way? Sure. All right, so now I can plug my values in. My M2 is what? 0.5, should I just call it big M? Or do I need to say moles per liter? Are we converting? No, let's just leave it big M. Now, do I have to change this to liters?
Depends on how you want your final answer.
That's it. It depends on how you want your final answer. So let's just leave it as is. Times volume 2, which is 250 milliliters, divided by molarity 1, which is 12 molar solution. What cancels? Molarity, and we're left with milliliters. So like Victor says, if we're okay with milliliters, just leave it there. If we want liters, then change it by converting. And so we do 0.5 times 250, divide 12, and what do we get? I used a wrong unit, so I don't have it in my notes here.
10.416 repeating.
What is it?
10.416 repeating.
What do we say? 10.4 milliliters. That a lot or a little? That's just a little bit, right? Okay, did we make this solution yet? What do we have to do to this? What?
Going back into our original equation, I guess? I don't know.
No, we're actually physically, literally making this stuff. How do we do it? We just calculated that we need 10.4 milliliters. So we got our little container here, and we put 10.4 milliliters of my concentrated solution of hydrochloric acid here.
Do we fill up to 250 with water?
There you go. Fill it up the rest with water. That's what we're doing. We're diluting this, right? So can you calculate how much water you need? 250 minus this, right? Yeah,
Shouldn't we run the 10.4 to just 10 as a sig figs?
maybe. but is this our final answer? We're just saying, how do we make this stuff? But, yeah, we would. But again, we don't round until the end, because if we did round, and we just said 10, would that make it more or less concentrated? Less concentrated, right? If we need that exact concentration to get as close as we can, right? And sig figs are great for calculations, but when we're doing this in real life, yeah, you get as close as you can. Because that's the purpose of sig figs. So don't let sig figs rule you. Okay. Yeah. Yep. All right, we good? Because exam is just theoretical, right?
So the answer is just 250 minus 10.4, and then that's how much water we need?
So that's how much water we need, but this is also part of the answer.
Right, it should be both.
So if we're saying, how do you make this? We're going to need 10.4 milliliters of 12 molar solution HCl with, what is that? 200 and what?
239.6.
239.6 milliliters of water. Okay. Does that make sense to everybody? Did I lose anybody? Okay, then there's some practice dilution equation in section 5. Do you want to do another one?
Yeah.
Okay, let's just do this first one. If you want to choose your own and do your own, that's fine. Okay, so we have a volume. We have 50 milliliters of 2.0 molar concentration of sodium chloride, and we wanted to dilute it to a 0.5 molar concentration of NaCl. So that means we need to find out how much what?
Volume?
Yeah, what volume will we have? Calculate the unknown volume or concentration, okay? So M1 V1 equals M2 V2, and we're solving for, we gotta label these, right? Which one should we say is M1?
Polar first.
Yeah,
Our first number.
we're starting with this, right? And this 50 is V1. Then the 0.5 is M2, and we're looking for V2. Do you see? Oh, it's a different one. Dang it. Can we just flip them and just use the same equation?
Yes.
Sure, we could. Okay. But we'll just keep it straight. So solve for V2. We divide by M2 to both sides. And now plug our values in. M1 is 2 molar. V1 is 50 milliliters. And M2 is 0.5 molar. Molarity cancels out, leaving us with milliliters. And that's okay. It doesn't say to put it in liters, so we're fine. And we got 100 divided by a half. That's 200 milliliters. That's it.
Is that the amount of water we need? Or is that
No,
the whole-
that's how much of this new concentration we will have. So how do you make it?
So we'll need 150 milliliters.
We add 150 milliliters of water to that, and we got it. Make sense?
Yeah.
Questions? Okay, that is our break time. We do have, maybe we won't get out super early, sorry.
Too many questions.
What?
I said too many questions.
And that's okay. No problem. Okay, take a break. And we'll start on different units of concentration.
Did I have a bad time this weekend?
Is there a lot?
Yeah, fuck yeah, there's a lot, and it sucks.
All 4 days
I've noticed there's a lot of, this energy stuff is fine to me,
Mhm.
but there's a lot of conceptual questions with graphs like this,
Mhm.
and I feel like it's just a whole lot of nonsense. Is that something I'm gonna have to stress about for our exams, or not really?
I don't,
Let's see. Yeah, like stuff like this,
no, you won't.
like it gives us these energy
So
levels and
this is
then
what we went over
molecular
last time, and
orbitals.
it's not on there. It's
Okay.
not. But we went over that last time. Do you want me to kind of show you here?
Truthfully, I don't care.
Alright, your call.
Okay, I just wanted to be sure if that was something I did actually need to understand and internalize to do well on our exams, or if it was just
Yeah.
real kind of nonsense.
Yeah, what seems like when I took it, we did talk about bond order and all that stuff, and seems like I went away with a, what? Cause that, they do this and then they don't touch it ever again. It's like,
Okay.
alright, why do we do that? But yeah.
I wanted to ask too, with polarity, we worded it in class how specific bonds can be polar, but not necessarily the whole molecule. And so it depends on both electronegativity and symmetry.
Shape,
Right. Okay.
more importantly is
Symmetry.
symmetry.
Yeah.
Do you have a question?
Because this molecule to me seems like it is not symmetrical, but it is.
But if you draw.
Because when you draw it bent,
Yeah.
yeah, we did talk about this
Yeah.
one. Yeah, it's all good. Okay. And I feel like this was just pure luck, guessing the best structure, so to speak, depending on
Okay,
formal
So-
charges of each.
yeah, so this has,
I even drew it out, and did the individual charges of each of them. Yeah, they all balance out to 0, but what makes this more stable than this one?
because,
Does that make sense?
yeah, so they're always gonna balance out to 0. They, unless you did it wrong, okay? But this one right here has a formal chart, 1, 2, 3, 4, 5. Normally it wants 6, right? So that adds +1, it had to lose an electron. And this one has +1 because it had to lose an electron. And this one has 1, 2, 3, 4, 5, -2. Which one's the most electronegative? Hold on, it says this one's better?
No, it's a structure of 1.
Oh, okay, I see. Hold on, that one's not better. Okay, yeah, this one has +2. Which one's more electronegative out of these guys? That one is. That one, if any of them have a formal charge, that one should be negative.
It's more electronegative because it has a positive charge.
No, it's more electronegative because it's closer to fluorine. It's electronegativity, so, right, this has a 3.5, this is 3, and this is 2.5. So this one's more electronegative. So if anything, that should have more electrons rather than this one has more electrons. That's why that one's probably the worst one.
Okay.
This one's better because this has a formal charge of 0, formal charge is +1, formal charge is -1. And this one over here, 1, 2, 3, this is formal charge of 0, formal charge of +1, and -1. So this one is ideal because this one has a -1 formal charge because it's more electronegative.
Oh, okay. So, okay, that makes sense.
And
Electronegative.
and
Whichever one is
is it
electronegative
easy
should have-
in your mind to see which one has a formal charge?
No, I have to do the math. I have to think
Okay.
about the equation and then think through it, but,
Look at the periodic table.
yep.
Oxygen has 6
Six.
valence electrons, 1, 2, 3, 4, 5, 6, 7. This one, one from oxygen, one from nitrogen. That one has 7, one more, so it's 1 minus. It gained the electron. This one has 4 by it,
Yeah,
so
one's 5.
it wants 5, so it's +1. This one has 4, so 0. And then you don't have to do all the math, you just look at it and,
Alright, that actually makes sense. Okay. That stuff I think is fine. If I have my Vesper handout or whatever, I can do that.
you know.
Yeah, that's fine. Fine. I find these annoying, but I can do it. This guy, the first time I went through, I picked this guy, because that's what I drew.
Mhm.
And then it told me, no, you're wrong, because it's an ionic setup. So then I thought, okay, if I think about them in terms of ions, then it does look like this guy.
Yeah. Yep.
But I
that's
feel like
it.
we didn't talk about that in class necessarily.
No. So
Like we just
I
always drew
I
the
did
Lewis
mention,
structure regardless of whether it was,
no,
ionic
we
or
never did it
covalent.
for ionic. So I did mention that the Lewis structure is for only covalent compounds.
okay.
That's all I did. I didn't bring examples out, but yeah.
All right, then that's fine. Okay.
Yep.
Okay, this has been a little confusing for me, and I think I understood it, but like, this is for my unit test kind of study thing, and I wanna make sure that it's right. So, the K, it doesn't have, it's not negative, right?
No.
Because in some
The-
parts
the
of my notes, it
equation-
says negative.
The equation is -K.
It is negative K. Oh,
So,
okay.
yes, the equation is -K, so there should be a negative right there.
Okay,
And
but K itself.
really, that just tells us if it's losing or gaining energy, really.
Okay, and for this, it would be losing energy.
So if it's out here and it jumps back, we're losing that energy.
Right, right.
But if it's coming here and it jumps out, it has to gain that energy to get out there. So if you want to get rid of that negative and think about it conceptually, you can.
But then the
But that,
equation
but
wouldn't work.
well, the equation does work. You just have to know negative means you lose it and positive means you gain it.
Because the answer in the end will just be negative.
Yeah. So I mean, you do need that negative, but anyway.
But it's always negative.
Yeah, because if this was the final, if the final was way up here and the initial was way down here, which one's going to be bigger? This one's going to be bigger, right? So you have a small number minus a big number, it's going to give you a negative. So you have to, so you're taking in energy, it's going to be a negative times a negative is a positive.
Okay.
That's why you have that negative. So in the equation, it's always negative K.
Negative K. Okay, I think that's what was throwing me off.
So put a negative right there.
Okay. And right.
Yep. Okay, we good? Okay. We have a question. Do you care if everybody?
It was just about like if I could, because I wanted to be like proctored on the exam because the last one I couldn't print out my notes well,
Okay.
and then they were impossible to actually read. So I was wondering if I could somehow use this, or if you could proctor me or someone else.
That's a good question.
Because I tried printing these out and it came out horrible. Like I could not read my notes at all. So I tried scaling it and it did absolutely nothing.
So
my iPad. Oh, OneNote. nobody really uses OneNote, so it comes out really bad.
I was gonna say good note, they come out like bad.
Look, yeah, for
And
mine,
you
it
tried,
makes
like-
a giant page, and then you, I mean. we
Can you,
tried
can you,
scaling it.
can you save it to a PDF or something?
Yeah, that's what I did.
Oh,
and
did
I
you?
tried printing it, and you can't even scale it to like fix it.
Oh, really?
Their app's just really bad, but
Um,
yeah, freaking sucks.
here, I mean, for the midterm and the final, you can't have your notes anyway.
Yeah.
So if you make your reference sheet and use it as you go,
Yeah, I've been building a reference sheet
Okay.
already for like the midterm, but like for these unit exams, it'd be nice if I could just have all my notes with all my solutions.
but no, that's what I'm saying. If you make your and I know that's all the way into it already, but if you make your reference sheet as you go, then you can use that reference sheet even for those. And I know that's
Yeah, but
kind of,
I just have so much information.
Yeah, yeah.
Into these.
so,
That's nice.
let's see.
I could screen record.
How long, how much time do you have on those exams?
An hour.
2 hours. Okay. Let's see. Do you have anything before class? Before this class?
No.
You can come and take it. I have a class that ends at 12:30. You can come in early and I don't know if that.
I don't know, didn't she say it closes on Sunday or something?
That's what it says on Canvas.
Yeah, that might be an issue.
Uh,
Unless we could open it every day or something.
I could.
Okay, that'd be nice. I'll send you an email about it, just
Okay.
see.
And okay, yeah, I'll do that.
Alright, thank you.
Yep. Yeah.
Why are the midterms and final not open note while the unit exams are? It just seems weird.
Probably because
To the testing center.
it is in the testing center. And that's all you get. But here's I mean, if you guys use that reference sheet for everything, it's gonna be cooler for you anyway.
Well, I'm not saying, I just thought it was weird that it would allow open note on some tests but not others.
Yeah. Well, it's kind of like, well, we want you to know this stuff, right? And if you're just relying on, and I know you still have a whole page of notes, so I don't know, it kind of goes against that anyway, but if you can get it down and tell us you know it on the midterm and the final, those are the big tests that we're looking for
Okay,
anyway.
alright.
Anything else that you want to complain about? No, just kidding. I just tease. Sorry. All right, let's move on to different units of concentration. So the first one after molarity is mass percent. How you guys with percentages? Do you know how to find the percent on your test if you know how many you got right?
Yeah.
Anybody struggle with that? Okay, well, that's how you do percentages, whether we're talking about percent composition, percent yield, percent error, percent whatever. And mass percent, no different. But this is also a unit of concentration. How do you calculate concentration? Amount of solute over amount of solution. When you're dealing with mass percent, what is the amount of solute should be measured in? Mass. Like that? Mass of solute over what? Mass of solution And then we gotta change it to percentage, what do we do? Times 100%. That's it. It's still a concentration. Now, the thing you have to know is the mass of solute and the mass of solution better be in the same unit. If you're measured in grams, they both better be measured in grams. You could do micrograms, but they both have to be measured in micrograms or kilograms or whatever. You with me? So an example of this is bleach. Bleach is 7.4% by mass of sodium hypochlorite. Sometimes they write it a little bit different than that way, but I don't like to. Are we good with mass percent? Should we try one? Okay. So let's say we have 3,000 milligrams of sucrose. This is table sugar. In 200 grams of soda.
What was your bleach example of?
It's just, so bleach, the stuff you bleach your clothes with, is 7.4% by mass of sodium hypochlorite. Just an example of what is measured in percent mass. All right, so what do we do here?
What are we trying to solve for? It's sucrose, right?
Percent by mass. That's what we want to know. We want to know the concentration in percent by mass, or mass percent we call it. What goes on top?
Massive solute.
Yeah, what's our solute? Sucrose. And our soda is our solution, right? Should we just times by 100 and we're done? No, they have to be in the same unit. What unit do you want it to convert it to? Convert them all to micrograms? No. Yeah, let's just keep it simple, right? It's easy to convert to grams. Well, either way, okay? So 1,000 milligrams to 1 gram. That goes away. Guess what else goes away? Oh, well, that's cool. They all go away. And that's the reason they have to be the same. Because then what do? Times by 100%. What's the unit of 100%? Of percent? Percent. Yeah, that's our new unit. We just call it percent by mass. And so we get 1.5% sucrose by mass. Good? How are we feeling on that? Pretty straightforward or talk to me. Okay? Now let's do percent volume. Bet you can't figure out how to do this. Almost. Times 100%, that's it. Volume of solute over volume of solution times 100%. And again, the volumes better be the same unit. An example of this is rubbing alcohol is 70% C3H8O, isopropyl alcohol.
Volume of solute twice.
I just wrote it sloppy.
Oh.
Sorry. Good? Let's do an example. Make sure this is solidified in our brain? Okay, if we have 156 milliliters of acetic acid, in 625 milliliters of vinegar, what is the volume percent? So tell me what to do. 156 milliliters over 625 milliliters. Don't be afraid to write those units down. We can see that they do cancel, but we need to see that. Okay? Otherwise, if they don't, well, we can't see it anyway. And then we're wrong. Then don't forget to multiply by 100. And what do we get? 24. Is it not 25%? Okay. Yeah, that's what vinegar is. It's about 25% acetic acid. Distilled vinegar, anyway. Okay.
What is acetic acid?
It is this. There's acetate, and it has the H plus in there. Do we talk about acids at all in this class? Okay, a little bit. Yeah. Well, we talked about the naming of it, right? Yeah. It's that yucky smelling stuff. Unless you like it, then it's not yucky.
So there's like 25% acetic acid in vinegar.
75% water by volume.
Is
Yep.
it only water and acetic acid? There's nothing else?
What's that?
Is it only water and acetic acid? There's nothing else in vinegar?
Well, I don't know. I don't think so, but you guys ever read ingredients on your stuff? Is that the sole ingredients, you think? Sometimes they say spices, right? What the heck are spices? Okay, there's stuff in there that they don't say because they don't want you to know because they're trying to poison us. I don't know. But okay, something. Okay, I don't know for sure. I'm just teasing. All right. We good? Okay, there's one more thing I want to show you, and this is, we deal a lot with aqueous solutions. We talked about aqueous solutions last time, right?
Yeah.
Okay.
Can I ask a quick
Yep.
question? Okay, so when you were talking about the isopropyl alcohol,
Uh-huh.
if it's 70%, then that technically isn't the solute, but it shouldn't really matter, right?
Yes, it's the solvent.
Or solvent, yeah.
Yeah, it is the solvent, but we still call it, we don't care how much water's in there. I mean, we do,
Right.
but
It
that's
doesn't
really
matter,
the stuff. Yeah,
Okay.
yeah. So that one's kind of a little bit different than most of the rest of them. Yeah,
The equation's the same.
yep.
Okay,
Are we good?
thanks.
Okay. Last one for percent is percent by mass and volume. Whoa. Can we do that? When? Because we did this so that the units could cancel out, didn't we? Milligrams, we did that so that units cancel out. Can mass ever cancel out with volume? If we're dealing with aqueous solutions. And in chemistry, most of the solutions we deal with are aqueous. So it is okay, but we have to know that the density of water is 1 gram per milliliter. If we use mass to volume percent, we have to use grams of solute over milliliters of solution, or vice versa, right? Has to be these units. Well, I guess it could be kilogram over liter, because that's just converted, right? but a lot of times we deal with grams and milliliters anyway. So this is equal to grams of solute over milliliters of solution times 100. And we can do that because 1 gram is equal to 1 milliliter. And so they do cancel out. Make sense? Any questions?
You said this was only for aqueous solutions?
Yes. Why? Because water is the only thing that has the density of 1 gram per 1 milliliter. Okay? Any questions on percent solutions? Okay, there's 2 other types of units that we're going to go over today, and they all have to do with a very, very, very low concentration. We use these when we're talking about a very low concentration. That's parts per million and parts per billion. So parts per million, we just say ppm. And parts per billion, ppb. So here is the formula. For parts per million, well, let's use a different color. It's equal to parts of solute over parts of solution. Hold on a sec. What do we mean when we say parts? You guys ever paint and mix paint to get a certain color? And it tells you parts per parts, right? What are parts?
Ratios?
Well, so parts per parts, that is a ratio.
Particles?
But parts could be particles. But who wants to count how many particles you have?
So you're talking about moles?
What?
Are you talking about moles then?
It could be moles. Who wants to measure moles? Wait, we can't.
X per X.
It could be ounces per ounces, right? That's if we're doing a little craft at home, right? But if we're painting a whole building, we might want to do gallons per gallons, right? So it doesn't matter what unit we use. Well, it kind of does. We can use grams. We can use mass to mass. We can use volume to volume. What else can we use? Grams to milliliters if it's a water solution. Same thing, right? But now it's not a percent. So it's going to be mass or volume of solute over mass or volume of solution. Then we got to do one other thing. We got to multiply it by 1 million. Million, as in scientific notation, is just 10 to the 6th power. Okay? Can anybody tell me what the formula is for parts per billion? That's it. Same exact thing, just times 10 to the 9. So let's do this action. Can you guys do that? There we go. Does that make sense? So let's do an example. Are you ready for an example? Okay.
Million is mega and 9 is
As tera. No, giga. So the max level of chloride in tap water is 250 parts per million, according to the EPA, right? And this says that's okay, right? But according to the EPA, that's the maximum before it becomes dangerous, I guess. I don't know. If it's dangerous, leave it out. Okay. Okay. So we want to know if, let's see, we measure in our water that there's 300 micrograms of chloride in 1 liter of tap water. So does it pass inspection? What do we need to know here? No, that's okay. That's okay. We're good. We're good.
we need it in the right.
Right units. So I'm going to just start with 300 micrograms of chloride to 1 liter.
That weird U-shape symbol?
What?
Is it micro, that weird U-shape symbol?
Yep.
Oh, it looks like an M, but you did do the.
It kind of looks like a U too.
Oh.
Yeah. Okay, so liters of tap water, which is solution, right? I can multiply by a million, or let's hold off a minute, right? Let's make sure we have the right units. What do you want to convert micrograms to? Grams. So 1 million micrograms is the same as 1 gram. Good, that goes away. And I should say this is chloride. And then we want to change liters to milliliters. 1 liter is the same as 1,000 milliliters. And since this is a water solution, hopefully, right, then grams is going to cancel out with milliliters. We're good. You with me? Now what do we have to do? Times by a million.
So for parts per billion, you always want the volume in milliliters, not liters.
If you're doing mass per volume, the mass, and this is mass to volume percent, parts per billion. Mass in grams, volume in milliliters. Or what's even better is mass to mass and volume to volume, right? Yeah.
Since you're saying it can be kilograms to liters, does it essentially just need to be proportionate units?
Yeah, the reason it could be kilograms per liter is because that's still the density of water, right?
So we technically could have converted micrograms to kilograms?
Sure.
Oh,
Yeah. Mm-hmm.
sure. Okay.
Yep. All right, and then we do this and we get 0.3 parts per million. Are we good? Yeah, it passes. Questions?
So is this saying there's, in 1 liter, there's, no.
This is saying there's 0.3 grams of chlorine for every million liters or milliliters of chlorine. Yep. And if we did that, if we did 0.3 grams of chlorine per 1 million milliliters of solution, and then we times it by 1 million, well, that goes away and we get 0.3. Make sense? Okay? Ready for another example? Okay. Okay, maple syrup has a contaminant level of 7 parts per billion. What mass of contaminate is in, so what mass of our contaminant is in 5 liters of syrup? We know the density of maple syrup is 1.33 grams per centimeter cubed. Do you guys remember how to convert centimeters cubed to other units? Yeah, 1 centimeter cubed is the same as 1 milliliter. So we can just move that and say per milliliter, right? A little easier. All right. So we got to find the mass of our contaminant in this maple syrup. What do we do? Seven parts per billion is equal to here's our formula. We're just using the formula.
7 grams over 1 billion.
So this is going to be mass of contaminant. We don't know what that is, right? Over volume, but it should be measured in grams, because this isn't a water solution. So we got to change 5 liters, or we can say 5 liters is how many milliliters? Whoops. I won't skip steps. So 5 liters, let's convert this to milliliters first, right? Y'all with me? Why I do this? Because my density is measured in grams per milliliter, and I need to know how many grams, because I got to have grams per gram. This is not a water solution. I can't use grams per milliliter. You with me? Only do grams per milliliter for an aqueous solution. So 1 liter is the same as 1,000 milliliters. And then here's our conversion factor density, 1.33 grams per 1 milliliter. And that gives me what? Six 650 grams. You with me? So that goes right here. Any questions on this? Did I lose anybody? Yeah.
What is that symbol? Looks like it on the left, something equals,
This?
yeah,
That's a 7.
what's that?
Because it's 7 parts per billion,
Okay.
right? And I just threw it in the formula. The formula says this right here. My parts per billion is 7. And then I use the rest of the formula. Great question.
The density was given, right?
The density was given to us and would have to be given that. Okay? And so now we can, what? Solve for x. Divide both sides by 10 to the 9. and then multiply both sides by 6650. Everybody following me there?
Okay, where did you get the 6650?
Right here. I converted, we have 5 milliliters of syrup,
Got it.
and I used the density, convert that to grams. What's that?
47 million?
47, 1, 2, 3, 4, 5, 47 millionth of a gram. So we can say 47 what? Micrograms?
Say milliliters, microliters.
Why not use 1 sig fig? Using 5 liters.
Yeah, so 50. And I skipped a step, sorry. So if we do this, we're gonna get 0.00004655 grams, right? That's icky. Let's convert that to micrograms. 1 gram is the same as 1 million micrograms. 1, 2, 3, 4, 5, 6. So that's where I got 47. But if we have to have 1 sig fig, 50 micrograms. Does that make sense to everybody? Yeah.
We might have already answered this, but the 6,650 grams, what does it exactly stand for? Is that like the amount contained?
That's grams of syrup.
So it's, we just have that many grams of syrup.
Yeah, because I started with 5 liters of syrup. Sorry, I should have wrote syrup right here. Yeah. Any questions on that?
Will you do another one that's not an obvious solution? Please.
Uh-huh. So we have, this is our first one, section 7. 5 milligrams of sodium chloride. Whoop. Dissolved in 2 kilograms of solution. I want to know how many parts per million we have. So what do we do? This is the concentration. How do we calculate concentrations?
The solute by the solution.
Yeah, 5 milligrams of solute, in this case it's sodium chloride, per 2 kilograms of solution. Do I times a million yet? I could, but I gotta convert units anyway, right? I like to do that first, but your call. What do we convert to? Grams? Yeah, let's convert both of them to grams, right? So 1,000 milligrams is the same as 1 gram. That goes away. And then 1 kilogram up here to 1,000 grams. And grams goes away. And so does kilograms. Woohoo! Now what do I do? Times by 1,000,000. And if you can see this, guys, this is 1,000,000 right here, yeah? You can just get rid of those, and it's 5 divided by 2, it's 2.5 parts per million. Doesn't always work out that simple, but can we convert that to molarity? Maybe not. We don't have density. But sometimes we can. Like if an aqueous solution, if we have mass per milliliter of solution, we can convert milliliters to liters and mass to moles. Good? Should we try one? Converting from one to another? Sure. All right, let's look at our worksheet, section 8. Here, I'm hearing a lot of silence. Does that mean we're getting this or not getting it?
I'm sleepy.
Okay, fair enough. Okay, let's do, which one do you want to do? Pick one on section 8.
Let's do the middle.
Okay. 10% by volume of C2H6O, and we have a density of 0.789 grams per milliliter. We want to know what it is in molarity. Okay. So we have the percentage here. Should we just use the formula for volume percent and plug it in? 10% by volume is volume of that one's not going to work out so hot. Let's change this to be mass to volume. That was a bogus one, sorry. Didn't give you enough information. So we have mass, and we can say grams, right? Grams of our solute of X grams of solute of C2H6O. Hold on. Do I give you enough information here? Yeah, I think I do. Over milliliters of solution. And it's actually per 1 milliliter, right? Grams per milliliter. Good. Times 100%. So we can figure out the mass by dividing both sides by 100%. So we got 0.1 equals X grams of C2H6O per 1 milliliter of solution. And multiply 1 milliliter of solution to both sides. So I have 0.1 milliliters equals X grams of C2H6O. So that means I have 0.1 gram per milliliter. Does that make sense or no?
I'm lost.
Yeah, it's a tough question.
Yeah, that one was kind of rough. Let's find one that's better. Let's do 500 parts per million of KCl to mass percent. So what do? Put that into our parts per million equation. 500. Well, in fact, here, let's just do it this way. What does 500 parts per million mean? 500 grams of solute per 1 milliliter of solution. You with me? Okay. That's what that means. Not 1 milliliter, sorry. 1 million milliliters of solution. I'm not going to, and then what am I going to do? Just multiply by 100%. Is it okay? Well, if this is a water solution, it is. And if it is, we could just call that a gram, right?
KCl water solution.
KCl is a salt, and normally it's dissolved in water in this class. So there's not a whole lot of information on this sheet. My bad. And so 2 of those zeros go away. And we have 2 of those zeros go away. 5 divided by 100, 0.05%. No?
So that's always true, parts per million equals grams solute over 1 million milliliters, right?
So all we're doing is finding a percentage. 500 per million. That gives you a decimal. Times by 100, that gives you a percentage.
Oh.
Sorry, I was just calculating without a calculator. That's all it is. Okay? Any other questions? Okay. Ladies and gents, do we have any questions on the exam? Because we got the exam this weekend, right? Anybody look at that study guide? Questions? If you don't have any questions, you're free to go. We're done with this unit. It's on the home page. If you go to the home page, it's right at the top. It says worksheets and it has the keys.
So the track sheet, do they have
You're okay. So remember, due dates aren't in stone, but don't push them too far.